SPring-8 is used by researchers from throughout the world in fields as far-ranging as materials science, life science, earth and environmental science, and many others. SPring-8 has also been used in nano and biotechnology development and other industrial applications. SPring-8 has been involved in a number of significant and remarkable findings, including the following industrial applications. In the fields of electronics and information science, ultra-thin insulation films that are as thin as a few atoms have been developed and analyzed at SPring-8 in response to smaller LSIs with enhanced integration. Magnetic disk heads, which consist of many layers of ultra-thin insulation films, are used for readouts. Conventional equipment is inadequate for verifying whether these thin films are correctly fabricated. However, since synchrotron radiation produced at SPring-8 has a high transmissivity and high directivity, non-destructive analysis of these extremely thin films is possible with precision up to 0.1 nanometers, which is roughly the size of an atom. These studies, performed at SPring-8, have contributed significantly to the achievement of high product reliability. Moreover, work at SPring-8 has also elucidated how these thin films are layered. For example, it was discovered that atoms are diffused at the interface between the thin LSI insulation film layers. In addition, as semiconductor devices become smaller, even minute metal contamination on the silicon wafer can cause problems. Conventional methods can only detect 300 atoms per 10 square microns, but a detection sensitivity of 100 metal atoms or less per 10 square microns is necessary. Actually, SPring-8 could detect as few as 4 metal atoms per 10 square microns. Further integration should occur in the electronics and information technology fields. Therefore, the significance of SPring-8 should increase dramatically in the future due to the unique opportunities available there to analyze materials on the atomic and electronic levels. The automobile industry is a broad-based industry that involves a wide range of technologies. Synchrotron radiation at SPring-8 has contributed greatly to research and development in numerous fields related to the automobile industry. In general, the performance of the catalyst that cleans exhaust gas decreases with use. A new catalyst, the intelligent catalyst, has been developed that maintains its initial performance level over time. Initially, the reason for the sustained performance was unclear, but it was revealed upon examining the atomic structure of the catalyst at SPring-8. It was found that the metallic atoms of the catalyst moved into and out of the crystal grains during the redox cycle. This movement would prevent the metal from coagulating and growing larger. Thus, the specialized catalyst is able to maintain its initial condition indefinitely. This catalyst is already being used commercially, which is helping to save precious metal resources. SPring-8 has also helped to determine why battery capacity fades over time by observing the charge-discharge cycle on the atomic level. We found that degradation is caused when the crystal structure, which initially consisted of deformed octahedrons, changed due to repeated charge-discharge cycles to become more regular. This finding has allowed the substantial extension of battery life, which has significantly contributed to the development of hybrid and electric cars. Synchrotron radiation is also useful in developing bumpers and tires. Bumpers are made of a buffer material that consists of foam aluminum. This video shows how the buffer material is crushed during a collision. Observing the deformation process of the foam aluminum is difficult with conventional X-rays. However, synchrotron radiation is sufficiently powerful to make such dynamic observations possible. Synchrotron radiation can capture how glass fibers that are blended into studless tires bite into ice. Such images cannot be obtained with conventional X-rays, which penetrate ice, glass fibers, and rubber in the same manner. In comparison, synchrotron radiation at SPring-8 is sufficiently parallel that even the slightly different refractions of these three elements results in increased imaging contrast. Proteins constitute the major building blocks of living organisms. In order to develop drugs that bind to and affect biologically important proteins, it is necessary to determine the atomic structure of these proteins. The first step in such structure determination is the growth of protein crystals. Growing crystals that are large enough for conventional analysis is time-consuming and requires much labor. Conventional methods required crystals as big as hundreds of microns. SPring-8, however, being considerably more powerful and sophisticated, allows the use of much smaller crystals, on the scale of 10 microns or smaller. Furthermore, complete datasets can be acquired in only several hours instead of several weeks. SPring-8 has already been used to determine the crystal structures of a number of proteins, including a macromolecular assembly that has millions of molecular weight. Detailed structural knowledge of disease-related proteins will aid considerably in designing chemical compounds that bind or react specifically with such proteins and lead to the development of clinically useful drugs. Studies at SPring-8 have helped to develop drugs that are used in cancer therapy, immunosuppression, hyperlipemia treatment, and other medical fields. SPring-8 has been used for research and development of industrial materials including metals, textiles, glass, and cement. It has also been used in energy industries, as well as for research and development on daily necessities such as food, shampoo, shaving cream, and water. Synchrotron radiation at SPring-8 is also used for forensic investigation and archaeological authentication of unearthed articles. For example, X-ray fluorescence analysis is a highly sensitive and non-destructive method for such analyses. It requires only minute quantities to identify the elements present, including heavy elements, which are difficult to analyze with conventional low-energy X-rays. Forensic studies performed at SPring-8 helped to identify arsenic in the curry poisoning case in Wakayama Prefecture. In archaeological research, synchrotron radiation was used to determine the composition of the Sankakuen Shinjukyo mirror that might have been used by the ancient queen Himiko. Synchrotron radiation produced at SPring-8 illuminates an atomic world that is otherwise invisible. SPring-8 is open to researchers worldwide and will continue to be a valuable tool for discovery in various scientific, technological, and industrial fields, including material science, life science, earth science, environmental science, nanotechnology, and biotechnology. Synchrotron radiation is a dream light that can illuminate the micro and even nano world. SPring-8 is a world-class facility that promotes and underpins the development of science and technology in the 21st century.